Hello and welcome to Practical 3, which is on earthquakes, lightning, tsunamis, and waves. So for this particular practical, you'll notice it is fairly freeform in that I'm reasonably confident most people could take it and run with it and do a lot of it themselves. However, what I will do in this recorded prac is to run through some of the key points and talking points where we stopped with the internals and had a chat about some of the answers. Now, what I won't do is give you all of the answers in this, although I'll probably blurt out a fair number of them. But of course, the practical answers will come out eventually after the practical quizzes are all complete. So, to move on with this anyway, the first section in this practical is lightning. And in particular, we're considering how you work out where lightning occurs, how far away a lightning strike might be, based on the sound difference between when you hear the thunder and when you see the lightning strike originally. So, for instance, normally you'd see the flash of lightning and then you'd hear the thunder. If you hear thunder at a very low rumble, the maximum distance you may get to hear it is around 30 kilometers away. Now, the speed of sound in air is about 344 meters per second at 21 degrees, and the first question in this prac is to get you to consider any factors that may actually produce a change in the velocity of the sound in the air. Now, you may notice we've given you the velocity at 21 degrees, so potentially the first thing you'd think of is perhaps temperature changes the velocity of sound in the air, and of course that's true. You might then think of other atmospheric indicators such as pressure, or velocity. You may even think of other factors such as humidity or wind speeds as well. So give that a little bit of thought because there's a big analogy between sound in air and sound in the earth, which we'll talk about eventually with earthquakes. The other thing which is worth talking about is the degree to which different sounds are absorbed in the air. If you hear a thunderclap and it occurs right overhead, it's a very sharp, dramatic sound. Thunder much further away sounds like a dull, low-frequency rumble, and the reason, of course, is that low-frequency sounds travel much further than the high-frequency sounds. We ask you to think of other circumstances where this effect can be observed. A classic one I like to point out is if you see some live music in a venue, inside the venue the sound engineers have it geared up so that the bass, the vocals, the guitars are all perfectly leveled for inside that venue. The moment you walk outside the venue, though, the one thing you can hear above everything else, of course, is the bass. And if you're a neighbor 5 kilometers away, that's about the only thing you can hear at that distance is the bass sound coming through. So, things to think about, other circumstances, you might like to think of the animal kingdom. Whales use this effect quite dramatically, so you may want to Google humpback whale or blue whale songs and the distances at which those animals communicate. And if you want to spend a great and instructive 10 minutes YouTubing, definitely Google elephants and infrasound and how they communicate through the earth using infrasound and detecting those vibrations with their feet, which essentially makes elephants large walking seismometers. Very, very cool. Right, so for us though, what we're interested in is the longer the time delays between when a lightning strike occurs and when you actually get the thunder coming through, that gives us an indication of how far away the lightning actually was. So for instance, you can actually plot this up as a graph, and we ask the question for a lightning strike 10 kilometers distance, what's the delay time? So if we're at 10 kilometers distance, we drive up to this part of the graph here, we intersect the line here, and we go across. We can see the delay time is just under 30 seconds, about 28 seconds. So if you counted 28 seconds, you know that the lightning strike occurred around 10 kilometers away. For us then, if you took that answer and 10 kilometers, you divide that by 100, that's 100 meters. What would be the delay time? Well, in that case, 100 meters, you'd divide your answer here by 100 and you'd end up with about 0.3-ish seconds or so, which is your delay time for 100 meters away, which of course suggests when you see the light and hear the thunder all together, the lightning strike's occurring very, very close by. Right. So moving on, we have a little bit of discussion section at the end of the lightning one where we're talking about most deaths from lightning occur between November to February. You might want to think about why that is. The hint I'll give you is wet season or monsoon season in the tropics. That applies to a lot of the East Coast. And the other point here is the number of deaths have fallen over the last century. In the past few decades, it's been about 2 per year. The question is why? Why do less people die from lightning now? Now, within the internal class, the factors you might want to think about are lifestyle. Where do people spend more of their time now? Jobs. What sort of jobs do people mostly do now compared per capita 100 years ago? Transport options available to people, and even engineering solutions. What do we do when we build or design transport now that may give us some measure of protection against lightning strikes that didn't exist 100 years ago? Right, I'll leave those open for you guys to consider, and we'll move on to the earthquake section now. So this part of the prac is an absolute classic that you end up doing at every single introductory earth science course anywhere in the world, and that's finding the epicenter of an earthquake using triangulation. So in order to do this, we have to work out how far away the earthquake is from a recording station, and we do this by capitalizing on the fact that different earthquake waves travel at different speeds. The fastest are what we call the P waves, the pressure waves. That's what you're hearing from me right now. P waves are sound waves, effectively. They're a compression in the medium they're moving through. S waves are the secondary waves, or shear waves. They require the medium to actually be able to bend a bit elastically. And as they bend out of place, they snap back in a kind of sinusoidal fashion, just like an S. And that enables the wave to travel through. Now, as you can imagine, something has to be somewhat elastic in order for that to work. It has to be able to bend back to its original position. So S waves can move in things that have elasticity, like solids. They can't move in things that aren't elastic. If I tried to bend the air a little bit out of way, it would just flow. It wouldn't snap back into place. It has no elasticity. So, when we think about the factors that might control the speed of both, you may think back to the thunder question and say, oh, temperature, pressure, maybe even humidity, and all of them are right. Even water content of the mantle is important for these wave speeds. But they're right in that they really affect a couple of key properties of rocks. One you might mention is density. That absolutely affects wave speeds, although in a little counterintuitive way. The main thing that affects wave speeds, though, is, as I mentioned, these waves travel often elastically through the Earth. They require deformation of the medium they're traveling through. And the way in which we describe that deformation for rocks is with a property called their rigidity. So the rigidity describes exactly how elastic a rock is and how likely it is to deform, and also then prescribes what the wave speed is through the rock. Right, let's move on now. We've actually got a seismogram here to show you, which was it's showing an earthquake that occurred in Turkey back in 1999. So what you can see here is an old school seismogram where we start at 4 a.m. in the morning here, and as we go across this line, this is 4:10, 4:20, 4:30, 4:40, 4:50. At 4:60 it snaps back to 5 a.m. here, and there's another hour. At 6 o'clock it starts again here. That's another hour of recording. So each of these horizontal lines across is an hour of recording. When you have a big effect like this, you end up with the lines obviously crossing a little bit right here. So what we can see on this is the arrival of some earthquake waves in this particular seismogram. So this one is about 12 o'clock here. And what you can see is this little blip is our first arrival, our P waves, occurring at about 12:07. Then we see a little bit of effect from those, and then at about 12:21 we see the next big wave packet arrive, which is the S waves. And then a bit of noise, and then these big guys arrive at around 12:27. These are the surface waves. These are the waves that cause most of the damage in an earthquake. These are the ones that knock down buildings, destroy roads, etc., etc. So these are the damage-forming ones, but they also travel much, much more slowly. So first question then is, at what time do the S waves appear? So the P waves are at 12:07, the S waves are about 12:21 or so, and then the surface waves occurring here around 12:27. So you write those ones in there. Now for us, what's interesting is not the absolute time. That doesn't matter that a P wave derived at 1207. What matters is that the P wave derived at 1207, then the S wave arrived at 1221. That means there is a 14-minute difference then between the P wave arriving and the S wave following afterwards. And that time difference between the P and S waves is what's important here. So the analogy here is like for lightning and thunder. First your lightning arrives, and then sometime later your thunder arrives, and it's a time difference between them that's important. But instead of lightning, we've now got P waves, and instead of thunder, we've now got S waves. So we use that 14-minute difference, and now we've got this graph lined up here. You read off 14 minutes on this y-axis here, and you trace it across very exactly using your ruler, much more carefully than I am, to where it intersects this curve, and you draw a line down, and you can work out exactly how far away from the earthquake epicenter you are in thousands of kilometers. So this, for instance, would be around 12,000 kilometers or so, but obviously if you're doing this on a hard copy with a ruler, you can do that much more accurately. And then the question was, at what distance from the epicenter in Turkey was the recording station? So that would be around 12,000 kilometers. And which of the two records downloaded from the web is this likely to be, from either Yerevan in Armenia or Charters Towers in Queensland? So without looking at a world map, I can tell you Armenia is almost right next to Turkey, and so Yerevan's very, very close, within a few hundred k's or so, whereas Charters Towers, obviously in Australia, much, much more further away, and this is much more likely to be in Charters Towers, being 12,000 kilometres distant. Okay, what we've got next then is a record from a 2011 earthquake that occurred, and it was detected in these three recording stations in Taiwan, in Charters Towers, and also in Lusaka in Zambia. Now, the delay between the P and S arrivals was 5.5 minutes, 7.5 minutes, and 10 minutes. And what I want you guys to do then is take that 5.5 minutes, go back to your curve here, read off 5.5 minutes, go across and work out exactly how far away from Taiwan the earthquake was. And you'd write that answer in here. So this should be around 4,000-ish, but you guys do it very accurately. You do the same then for Charters Towers. You go and read off 7.5 minutes and you get the distance around here. And then you do the same for Zambia. You run off and get the distance and work out how far that was. Write the distances in there. Do it as precisely as you can with rulers, because getting it exactly right will be very important for getting the exact epicenter of the earthquake. Now, once we have those three distances, you can take, let's say Taiwan was about 4,000 kilometers. You can take a compass now, put the pointy bit here, and then the pencil here at 4,000 kilometers, and then you can stick your pointy bit here and draw a circle with a radius of 4,000 kilometers around Taipei. Now we know the earthquake occurred somewhere on that circle, 4,000 kilometers around from Taipei, but we don't know where. We need more information. So the next bit then would be to take your distance from Charters Towers, put your pointy bit of your compass here, your pencil where that distance ends up on this scale, and then using that same spread, draw the distance around Charters Towers where the earthquake occurred. Do the same thing for Zambia, work out your distance, put your compass, draw a circle around it, and what you should get, if you do the distances very accurately, is those three circles will intersect at one point and one point only, which will be the epicenter of the earthquake. Now you may be a little bit off because we're reading off a graph here, and that's going to introduce errors, but you should get them pretty close to the major fault system where this earthquake occurs, and you should be able to work out what country it's occurring in as well. So I'll leave that answer for you guys to work out. And the last section of the earthquake section here is asking, well, if we had an even greater delay for surface waves, would it be possible to warn people of the surface waves as soon as the P waves are recorded? Does this happen? One thing to think about here is, if we go back to our seismic trace, the surface waves here occur at 12:27, about 20 minutes after the P waves first arrive at 12:07. So we've got about 20 minutes warning, which seems reasonable. But of course, this is 12,000 kilometers away. This is far too far away for an earthquake in Turkey to have an effect on Charters Towers. What sort of warning would we get if the earthquake were much closer? Well, if we have 12,000 kilometers, gives us 20 minutes warning, and 6,000 kilometers, you'll have 10 minutes warning. So then you'd have about 60 kilometers would be about 2 minutes warning, and then for about 1 kilometer you have about 1 second warning. So there's a huge scale down then in warnings at the amount you get. So if you're within about 60 kilometers, which is about the radius of effect of a large earthquake, you're going to have a little bit of warning, about a minute or so, but it's not going to cause a massive effect out there. If you were within a kilometer, you're going to get in the order of a second. You might get 10 seconds, up to about 10 kilometers away. So is that significant? Well, 10 seconds isn't really enough time to run outside a building. In fact, it'd be ill-advised. It's enough time to maybe jump under a table or a desk. But for electronic systems, it could be useful in that if you had a high-speed train, like in places like Japan, that's traveling at 400 kilometers an hour, and it detected a P wave, and then knew there was an S wave coming which could potentially damage the rails, it could, in fact they do, cut the power and bring the train to a halt before those surface waves do any damage to the rails. So it could be used in automated system, but it's a very short delay between when earthquakes occur or first detected and when the damaging surface waves arrive, which is why they're so hard to create a warning system for. Right. Let's move on to tsunamis now anyway, so you can detect the trend here. This is also a wave, but nothing to do with the tide, as you may well know. Tsunamis are where the entire water column is moving. So as opposed to surface waves or wind-driven waves, which are just the surface moving, in a tsunami, the entire package of water, down to about 5 or 6 k's wherever the ocean floor is, that entire column of water is moving across the ocean. So with that sort of definition, what else might cause a tsunami besides an earthquake or tectonic plates? So I won't give you too much here, but a couple of hints here might be dinosaurs, if you think about what happened to them. Another hint might be not all landslides occur on land. You might want to think about the conditions under the Norway continental shelf or off the coast of Oregon, which have given us some enormously large tsunamis that have got more to do with the slope of the shelf than with earthquakes occurring. Couple of points of definition here is the wavelength, the wave amplitudes from the unperturbed height of the ocean to the crest, strictly the wave heights from the trough to the crest, so twice the amplitude. The shallow water wave equation, the velocity is then the square root of gravity times the water depth here. And this is the equation we're going to use here. Basically, it describes how fast a tsunami moves through the ocean. So for us, gravity is always the same, 9.81 meters per second squared, and d is going to be the water depth. So what we've done here is given you a range of water depths from the deepest parts of the ocean, the Marianas Trench, to your standard abyssal plain, average ocean floor, the depth at mid-ocean ridges, to the continental shelf, up to a near-shore environment. And what we want you to do is to use this equation, plug in G, which we've given you, but also plug in D from here, from this column, and work out what the velocity is in meters per second. I'll leave this for you to calculate. Your first answer, to make sure you're in the ballpark, should be in the order of 300 meters per second squared, not exactly, but close to that. Once you've worked that out, we want you to convert that then through kilometers per hour. The way in which you do that, as you read the hints, is you divide by 1,000 and then you multiply by 3,600. So take your answer here, which should be 300-ish meters per second. You divide that by 1,000, you times it by 3,600, and you should end up with a velocity somewhere in the order of over 1,000 kilometers per hour or so. So if you've got the ballpark for that, do that for each of these different ocean depths. And the last step here is to work out the time it takes to travel 1,000 kilometers. So here I've gifted you an equation where the time is equal to the distance, here it's the 1,000 kilometers, divided by the velocity, which is our second column here. So take your distance, 1,000, divide by your velocity, and write down the time here. It should be in hours. Some people converted it to minutes for the earlier ones, but I'm happy with hours if we leave it at that. Now lastly, then we want to consider if we were travelling at about 950 kilometers per hour, which is about the speed of a jumbo jet and the average speed for a tsunami in the ocean, how long would it take for that tsunami to get to Sydney from either New Zealand, Hawaii, or LA? Now, there was a world map a few pages back if you wanted to try and get the distances from those. You can also look at flight paths from Google from Sydney to Auckland, for instance, is a bit over a few thousand K. Hawaii is about 8,000, LA is about 12,000. Work out what those distances are and then use this equation again. So your time it will take will be equal to your distance divided by your velocity, which is 950 kilometers per hour. And write down your answer in there. It should be about the same time it takes to fly to those places. Then we've got the question, if we had a warning of about 1 hour, how long would we get for people to get to high ground from an even New Zealand tsunami, Hawaii, and LA, which is basically these answers subtracted by 1. But you can also see why a tsunami system is so effective for ocean crossing tsunamis. Now, the last bit we want to consider is why tsunamis get as high as they do. And the reason for that really is tsunamis travel phenomenally fast in the deep ocean, but they're only quite small, but they've got an awful lot of energy because the water column is so deep. As they approach shallow water, they slow down, and all that energy they've got has to go to somewhere. In effect, a lot of that kinetic energy goes into potential energy, or the height of the tsunami. So that's where it gets the energy to reach enormous heights as it approaches the shore. So the equation describing how this happens is what we call the wave shoaling equation, which looks like this. So for those of you who haven't done any maths for a little while, we won't inflict too much pain on you here, but just to kind of sum this up, A1 here is the amplitude of the wave in the deep ocean, which we've given you here is 1 meter. A2 would be the amplitude in your shallows, which is what we want to find out. D1 is the depth of the deep ocean, which we've given you here, 6,000 meters. And D2 is the depth of the shallows, which we've given you here, 200, 20, 10, 5, or 1. So you want to plug that into this equation in sequence and work out what A2 is. So in terms of rearranging the equations, if you haven't done this for a while, I did this on the board for the internals, but effectively you might realize that if you've got these fractions on either side, you can invert both sides of the equation. I won't go through the maths in detail here, but the final equation you want then, A2 is equal to A1, which is just 1, times D1 on D2 to the power of 0.25. If you do this in your calculator or anything, make sure you use brackets so that you're getting everything that needs to be in a brackets to the power of 0.25 in the right order as well. So that's the equation we use. If you haven't done this for a little while, feel free to work through the maths if you want to brush up your algebra. But essentially take that equation and work out the tsunami height for either 200, 20, 10, 5, and 1. You should get numbers always above 1 and probably less than 10 meters for the shallowest water depths. So that should give you some sort of sanity check there. Lastly, we want you to use this graph paper we've given you here to plot your water depth versus your tsunami heights. Now, water depths here are what we call the independent variable. They're what we've given you. They're the control variable. And the independent variable, by standard convention, always goes on the x-axis here. Your dependent variable, the thing that depends on this variable, goes on the y-axis. So your tsunami height should go here. So if you look at the range we've got, 0 to 200 should go along your x-axis and partition off accordingly. Your tsunami height, 0 to 10 meters, would be sensible once you get those numbers. Partition off. And then you can draw a little plot of how your water depth, as it decreases, your tsunami height will go up. You'll probably see that this is not a great way of presenting all this information, because you'll end up with a lot of points clustering up along one side, and then you may want to think about particularly moving into Prac 4 and your assignment of how best to present this data, and using perhaps a logarithmic scale on the x-axis may improve the way your graph looks, but not critical for now. Okay, that's the end of the practical anyway. I hope that cleared up enough for you guys to work through. Any questions, as always, just hit me up. Otherwise, I'll leave this for you guys to finish off. Cheers.